Alrighty. Let's mute that so we don't get an echo. So this is going to be the first time that we're trying the new Meet Echo thing. The way you're supposed to get in and out of the queue is using your phone. So there is a QR code that you're supposed to scan up there. Yep. So if you think you might want to get in the queue, you should probably scan the QR code so you can do stuff. Also, we have some set of people who are going to be presenting from here and some set of people who are virtual. The first presentation is going to be Jeff Houston, and he is virtual. We also have Justin and Eric Fink, who I think are in person. Is there a Justin and Eric Fink anywhere? Not yet. Well, they'll show up. Ignis, do we have an Ignis? We have an Ignis. Do we have a Lenny? No Lenny yet. Oh, remote. Okay. Willem, I saw a Willem. And Tony Lee is remote or virtual. Alrighty. Oh, excellent. So, I guess we will just jump into it. In case you're confused, this is IEPG. We're not actually an IETF working group, but we're somehow vaguely affiliated with the IETF. And let's do this thing. So I will start sharing Jeff's slides, and then
Thanks, Warren.
Welcome. And then I will hand the slide shareability to you, or you can just ask me to change them for you. But I think you should now have the ability to change slides yourself. And I will try and let you know if there are people in the queue as well or anything like that. So,
thanks, Warren. Oh, there we go. This is one of two talks this morning about IPv6 fragmentation and extension header behaviors. Why? Because there are a number of drafts out there that seem to think they're useful. They're probably wrong. Let's go find out. You know all this, no point repeating it. You know all that too, no point repeating that. You know, the only thing V6 really changed, if you get down to it, was just taking the fragmentation controls and basically setting the don't fragment bit to a hard on. So the only agent that can fragment a packet is actually the source. There's a kind of a philosophical question about whether you should ever see TCP fragments at all. Because after all, if the source knows that it's going to fragment the packet in TCP, why doesn't it just change the MSS and not fragment? But that's a different conversation. Let's assume we're fragmenting because, you know, we can. So that's now shoved into an extension header. Now, the last time this was looked at hard is RFC 7872, and that work was done in 2014 and 2015. Hi, Jen. I can see you there somewhere. And these are the results that they published. Now, the way they did this was actually sending the packet to the server and manipulating the packet and seeing if the server actually responded. And what they found for fragmentation, FH512, was bad. I mean, anytime you see loss rates of between 28 to 50%, you know it's bad. But it's a little more than that, because they also tried destination options extension header and the hop by hop options extension header using, if I read that RFC correctly, a pad 8 option. And oddly enough, destination options seemed to fare better and hop by hop was a little bit worse. So just remember those numbers, okay? You're going to be a test later. So got it? Thumbs up? Cool. You've remembered it. Well done. As I said, we will test later. That's really, really bad, by the way. You can't fragment with a fragmentation rate that high. You just can't. And so why? Well, firewalls don't like fragments. This is true. The whole thing about IPv6 path MTU is kind of broken because it relies on ICMPv6, which you actually can't authenticate. Some random router off the street sends you an ICMPv6 packet too big, actually means that all it did is it saw the packet pass by, God knows why. And so anyone can send you these messages. Why should you believe them? And the other part of this issue is extension header chains are supported variably. Okay, so there's a problem here. The extension header handling, because it sits between the V6 header and the sort of upper level protocol, the transport header, also means that some transport protocol aware processors, be they switches or whatever, find the wrong data at the wrong offset. You go, but why is network middleware looking at the upper level protocol header? Good question, because it does, because they all do. Why? Well, they're just curious, right? Simple curiosity, yes, or something else. Nevertheless, there's a whole bunch of these units that if they find something instead of the upper level protocol, they just drop it. So the issue about 7872 is that it's not where the traffic goes. It's the other way. When you send packets to servers, you tend to send short request packets and the servers send you large answer packets. And so it's not the user to the server that really matters. What really matters is actually the back path or the other path from the server to the user. Now, this is much harder to actually construct as an experiment because although someone might control the Alexa top 1 million servers, it ain't me. And so trying to get the servers to behave in odd ways is actually more challenging than you think. So what we did was actually try and take conventional servers, DNS and web, and actually write a packet wrangler, or to be more accurate, a packet mangler, that takes a conventional packet from a DNS server or web server and actually fragment it, and then send it onward to its destination as a client, however, right? And to make this work, of course, well, actually we did it, sorry, I've got the order of the slides the wrong way. We did this in 2017. And as you recall, the 28% drop rate in 7872, when we did this in a V6 measurement platform that uses online ads, in other words, detects eyeballs, small number of servers, massive number of clients, we found the fragmentation loss rate was marginally better, 21% drop rate. Fair enough. Fair enough. Come back again last year. Reworked the same experiment, but we kind of redid that packet mangler a little bit. The same kind of technique though. We're sitting in the middle of the TCP session close to the server. We shove all the outgoing packets through this dedicated middle box, and we're inside a TCP session. So we can detect if the client didn't receive the packet because the client won't hack it. And so we detect a hung TCP session by the fact that the ACK just didn't happen and we can't proceed onwards. The other thing we did, we were kind of curious, is we were wondering if, because we were using large initial fragments, it was actually a subtly different problem, because this is the first big packet sent from the server to the client. And so we decided to test a range of initial fragment sizes between 12 and 14, 16 bytes, varying them by strides of 8. We performed this as an ongoing experiment. There's a slide about how this is not as easy as you think. We're using libpcap to actually snarf and send packets. This is great. libpcap has no buffer space. And so the problem is you've got exactly one packet time to get something done. That doesn't work. So we spent a lot of time writing shared memory systems that implement a ring buffer for both incoming and outgoing packets, and actually did a V6 NAT to make all this work. The server is actually a normal old server. The client we have no control over, and the Wrangler has all this muck inside it to actually make it happen. So what did we see? Now, the blue line is the loss rate, averaged for the world. And it's no longer 28%, it's no longer 21%. And up until, a few days ago, it's coming down again to around 7.5%. So apart from the fact we stuffed up the experiment over the new year, it's not bad. It's not brilliant, but at 7.5%, it's certainly not bad. The map is kind of interesting as to where this happens. The green is good, the red is super bad, the white is there's not enough V6 to even measure at the time. Odd graph. But if you think about it, the folk who are doing super good, like India, are actually the more recent V6 deployments. So it seems to suggest that this fragmentation drop rate is network, not host. It's not the destination that's doing just dropping it. It's actually the network itself. And the more recent deployments using whatever more recent equipment is out there tend to do a whole lot better than the initial deployments, which are sort of more conservative, like France, for example. And I think even the American one's kind of mixed. Whereas, like I said, India and around the Middle East, a lot better in terms of percentage of drop rate. Okay, big surprise. This is the drop rate by packet size. 7%, in this case, 9%, 9%, blah, 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 blah. As soon as you get to 1360, it jumps up. Huh? No idea why. But larger initial fragments tend to be a lot worse. A lot worse. And I kind of broke this up by region. In the Americas, it's there, but less so. In Europe, it's strongly there. And in Asia, it's, a definite signature. Why, if you put the initial fragment size high, is the drop rate dramatically higher? Varies by provider. If you're in TELUS in Canada, nothing gets through. It's a 95% drop rate. Well done, guys. There is no such thing as a fragment in TELUS. They just get dropped. Whereas Bharti, and don't forget that sort of anomaly is us, not them. Bharti Airtel in India, which is a massive deployment, a few hundred million users, the drop rate's around 4%. So they're doing a whole lot better than the world average. In fact, they're doing a whole lot better than most folk. So again, why is this happening? Local security policies, slow path processing, you can read this as well as I can. Is this fragmentation drop because we're fragmenting? Is it because the extension header in the packet exists and it's dropping because of that? So the first way we tried to answer this was actually bring up the null header. I'm moving really quickly so I can see you at the microphone, but I'm going to get through this and then you have your chance to speak. So up to you, but I will go very quickly. This is the atomic header drop rate, which is the null fragment. It's in red. And as you see, there's a component of drop, which is, this is a fragment, I don't like it. And there's a component of drop that says, you put in a fragment header, even though it's not a functional fragment, I don't like it. And the atomic fragment drop rate certainly is high, 6%, but it's lower than the actual substantive fragment drop rate. It varies provider by provider. In Germany, the atomic fragment drop rate's constant, that's bizarre, and higher than the normal fragment drop rate. In Italy, it's almost non-existent, whereas the fragment drop rate is high. And in Australia, the fragment drop rate, when we started measuring it, is higher than normal fragments. The atomic fragment drop rate's higher. This shouldn't be happening. You know, why do all these providers have completely different, if you will, packet policies around the handling of fragmented packets between substantially fragmented, there's data in all the fragments, and atomic fragments? Nah, it's just a header filling up space. Didn't help, did it? We didn't really figure out whether this is a drop by fragmentation or a drop by extension header. So we thought, okay, we will mangle these packets to put in, same as 7872, a pad 8 extension header. So we tried this firstly on the destination options. The other reason why we chose the pad N or pad 8 destination option is that all the rest of the destination options look crazy, weird crap. And so this is the few that's kind of, doesn't matter if it's there. If the client actually gets the packet, does nothing. It's just padding. So the network shouldn't give us stuff, and the client who gets it shouldn't give us stuff. So if anything's going to get through, it's going to be a padding destination option. Yeah? Awesome. 94.5% drop rate. I'm like, you actually have to program that. That doesn't happen by accident. That happens because you've sat in your code and go, I hate destination options. And so it seems that almost every host, and certainly because these days most of the eyeballs are sitting on mobile platforms hosts have a particular loathing of destination options, whether they contain padding or presumably any other directive. But it seems that it's just, wow, awesomely bad. So we thought, okay, if that's the case, let's mix this up a little bit and try hop by hop, because, you know, maybe the network truly is being malicious. So there is a pad N hop by hop option. Yay. Pad 8, because we just chose 8. So did 7872. Seemed like a good one. Again, this is null. Nothing should be happening. So again, the network should just let it through, right? Wrong. 99.5%. Again, you really have to work hard to do that. You know, if that was our objective, some idiot would go, no, I'd let it through. But it seems like the entire V6 world says, no, we don't like this crap. Because I've never seen such a consistent response. Everyone drops hop by hop. That's brilliant, 99.5. So the issue is, over time, the handling of fragmented packets has gone from just unusually, horribly, toxically bad to, pretty bad. You're still bad. More recent deployments show basically better handling of fragmentation header, but hop by hop and extension headers, ain't nothing happening in the public internet infrastructure. So what lessons have we learned? Don't fragment. Don't rely on path MTU discovery, and don't rely on extension headers. And interestingly, if you are going to fragment, don't just give a big first packet and a trailing tiny. If you're going to fragment, be decisive. Make your first packet small or smaller. Go down to 1280 bytes or something and shove the rest in the trailing fragment. If you actually do just big packet, small trailers, you have a much higher chance of losing everything. So pick your MSS settings and TCP carefully. If you're going to fragment, keep it low. Keep it below 1400. It's a good idea. The lessons learned on hop by hop extension headers and destination option extension headers, that's easy. Don't. And if you want to see the current numbers, because this is working around about, I think we're doing about 6 to 7 million samples a day across the planet. That QR code will take you to this URL. This URL generates a daily report, and it actually looks at the state of fragmentation headers all the time. And I am done. Thank you. Back to you.
Excellent. Can you hear me, Jeff?
Yes, I can, Jared. Hi.
Excellent. Yeah, nice to see you. You covered it a little bit in the end, but I'm wondering how much of the V6 is because of the mobile networks specifically. A lot of the mobile networks actually they get tail circuits from different ISPs to backhaul to the towers, or from different carriers to backhaul to the towers, and often they have an MTU on those links that's less than 1500, even internally for V4, let alone for V6. And so the 1280 kind of seems to potentially explain that. But I'm curious if you have further sub breakdown of, if it came from the mobile carrier's IP space, from the ISP, or if it's just from their generic IP space.
Every country treats mobile differently. There are folk like in my country that do mobile and wired all off the one address space, all off the one piece of infrastructure. And quite frankly, you can't tell if a mobile device is doing Wi-Fi tag, attachments into a home, or if it's actually out there on the mobile network. Other countries are different. The basic observation is that these days, the bulk of eyeballs are behind mobile platforms, however they attach. And that's just the reality of the world. So in some ways, making that distinction between what's wired and what's mobile is getting less and less important when you realize that 90% of the users and probably 99% of the money is actually behind mobile devices. What you're trying to do, and I think you're right, is to delineate the ways of attachment. And you're talking about the radio networks as distinct from the wired feeder networks. The system that I use in ads finds that difficult to detect in general. Now, you could take the data that I've got here and apply specific knowledge to a carrier and kind of devise from that which AS has which performance, and you'd probably be right. But from where I sit, I find that very difficult to do. But, it's a good question. Thank you.
Excellent. Thank you very much, Jeff. And for anyone
it's a pleasure. Thanks.
For anyone who tried the QR code, that actually goes to V6 frags with an S on the end of it. If you remove the S, the URL works apparently. Just as a note. No worries. QR codes are complex. I don't understand how they work. Magic. So
yeah, exactly.
We have Eric Vink or Justin. I'm not sure who's actually speaking. And if you happen to remember what the name, there we go, that one. And this is also going to be related to that. I can do slides for you, or you can do. Oh crap! There's a clicker thing. I don't know where the clicker thing's gone. I'll do the slides for you. Okay. Or I can share it to you. Where are you? Where are you? Just here we go. I don't see the request. Why is it not showing up? Yep. Sounds like a plan.
Hi. Okay, can you hear me? Yeah. No?
And I don't actually know how I change the slides view because I don't have a clicker when I see your slides. No, you're not allowed to touch the other computer. They're very clear on that. Apparently left and right does it, so never mind. Great. Is that not working?
No.
Use this in the meantime, I will find this.
Thank you.
Technology's hard. Sorry, folk.
It's better. All right. So, hi everyone. Justin from Liège and Eric over there from Cisco. Today, let me introduce you to James. And I have to say that we are particularly proud of that name because obviously it opens the doors to a lot of fans. But anyway, next slide, please. Why did we come up with James? Actually, there is already RFC 7872, which was mentioned in previous talk. And actually, we wanted to basically present new, refreshed, and more complete results. And you probably heard in 6man that there is a hot topic about hop-by-hop options. And the question is, are they usable or reliable over the entire internet? And specifically, two drafts have recently been adopted. One to define processing procedures for hop-by-hops. And the other one is more about sending and processing all extension headers and define some limits on it. So obviously the goal is to make them more widely adopted and make them progress the way they are supposed to do. So the question is, what about other extension headers? And that's where James enters the stage. Next slide, please. Okay, so this is an overview of the topology we have used. We have vantage points on some parts of the world, and as you can see, we are still desperately searching for some VMs in Africa and somewhere in China or Japan or somewhere in that zone. So we have a lot of vantage points in Europe, 3 in America, North, and 1 in South, 1 in Australia, 1 in India, and 1 in Singapore. Next slide. And the methodology we have used, no black magic here. This is a trace route light technique, even though this is our own library, but still trace route light. And we just test each pair of VMs in both directions. And for each experiment, we use UDP and TCP because you never know what filter you can have on layer 4. And for the experiments, we have tested hop-by-hop and destination options. And we vary the size from 8 to 512. We have also tested routing headers from type 0 to 6 included. We have tested fragment headers, atomic, both atomic and non-atomic. We have tested authentication headers, no-next header, or with Ethernet, which is defined in RFC 8986, which is, I guess, if I remember well, something about segment routing for IPv6 and network programmability. And so for each experiment, the traffic we send, the prop traffic we send is marked as proposed in the draft here that you see in the slide. So we have published this draft recently also. And the idea is just to either insert an ID or an address email or something in a payload somewhere in whatever layer allows to, or easy technique that you know is just to run a web server on the address you are sending packets and just explain why you are sending such traffic. And so with this, you have a view, we'll see that later, of each result. So you can see that each routing header, extension header pass or don't pass. And we also try to attribute the drop responsibility, firstly per hop, and then obviously per AS. And that's where problems come. So problems first at hop level, because you have to probe as much as possible, but still you have to respect network, so you don't have to introduce too much burden. But why do we have to test a lot? If you see the first illustration on top, you see that the trace, the third hop, did not respond. Only the first and the second responded. So you could say, okay, maybe the third hop is responsible for a drop, or maybe it did just not respond, and maybe this is the fourth, or maybe it did just not respond, and so it's the fifth, etc., etc. It's responsible for the drop. And so, illustration on the bottom, you run the same experiment a few seconds after, and then, oh, surprise, you see that the fourth hop did respond. So in that case, you just can rule out the third hop from being responsible for the drop. And so you're back to the same principle. Maybe the fifth hop is responsible for the drop, or it did just not respond, etc., etc. So if you run a lot of tests like that, you can just correlate them and try to have that zone as smallest as possible. And this is one of the challenge to attribute the drop to an AS, because you have to make that zone as smallest as possible, and the best case obviously is 1, right? It might never happen, but anyway. And you have also corner cases here. The link between 2 AS. So an example is that the egress router of AS2 would be responsible for the drop, but the address of its interface is in the state of the first AS. So it would wrongly attribute the drop to the first AS while it's secondary. Or in the trace, if it has identified or not identified some AS number before and after the hop in question, and so you might or might not identify the AS. Yep. Yep. Because of the math story. So, as I said, so the second case is that you have. Oh, it's not working anymore. All right.
Does anybody have any AA batteries? These died as well. I think the batteries died.
Yeah, probably. Sorry. Hello. I'm alive. So, second case, identified or unidentified AS number before and after the hop. So as I said, you might have or might not have identified some AS number between before and after the hop in question. And so you might or might not identify your AS here. So the best case is that your interval spans only one AS, and problems come when your interval spans multiple, so more than two or more AS. Next slide, please. So for the results, op by ops options, they are unreliable. So we have the same, we are agree with previous presentation. The destination options, obviously, size 8 and 16, they pass, so they go true. While once you reach 32, they become unreliable. And so for a size 32, 93% goes true. So it's not that bad, but it's still unreliable. Once you come to 64, it's half that part, so 42%, and it goes wrong with bigger sizes. For the routing headers, types 0 and 4, they are unreliable. Again, unreliable, but still good. So 81% and 69% pass. But here, type 0 is deprecated, and type 4 is segment routing, so no big surprise here. And types 1, 2, 3, 4, 5, and 6, sorry, they go true. For fragment headers, atomic fragment headers are unreliable. We have 70% that go true. And for non-atomic fragment headers, they all go true. Authentication headers, no next header or Ethernet, they go true. And so that's the results part, but we also try, as I said, to attribute drop for per AS. And so this is still a work in progress, so I won't go too much into details here and show results because they are still not that stable. So you can have a look at the draft for more details. Next slide, please. About the next steps, so we have set up an operator survey. So if you are an operator and watching this, please just have a look, click on this and fill in the form. That will greatly help us, and we could correlate what we observed with your data, and we keep privacy, all right? We also plan to extend the topology. So as I said earlier, we are trying to find some VM somewhere in China or Africa. And we also plan to use a probing to destinations we don't necessarily own. So for instance, BGP, based on BGP prefixes or Alexa top domains. And we also try to improve the drop responsibility attribution algorithm, firstly per hop, so reduce that interval as much as possible, and then per AS. And one possibility here is to use BDR map IT, especially for the case with a link between two ASs. Next slide. So thank you very much. Feel free to have a look at this repo where we gather all scripts to generate probes, packets, and results from James. I guess I will take questions now.
Hi. Oh, it works. Really good information. The most alarming to me was your last slide, if you want to bring it up. If I saw it right, when it gets up to, I guess, next to the last, at 128, you're losing 95%. And at 32, basically, you're getting through about that same amount. Do we know why that size makes such a big difference? And is it a problem we can address?
So you're for what extension error? Destination.
Well,
It says DOH there. I think if I'm reading your slide right.
Obviously, it becomes bad because probably routers have some predefined sizes, and you are pushing layer 4 too far away. So maybe there are.
Is it an issue with ASICs chips, or have we not drilled down? Are the routers logging this, or I don't know how much detailed information you collected to come up with that, but it's alarming, I guess.
Yeah, but about details, not that much, because all we have is the response from the routers, and so all we can do is assume something.
So I'll ask, a leading question is there going to be a follow through to drill down to find out why and see if we can do anything about it?
Sure.
Okay, cool. Then I'm happy.
Okay.
Thank you. This is really good work.
And I mean, I'll stick myself in the queue as well. It seems that a fair bit of this is likely stuff like where you only ship the first part of the packet to the forwarding engine, like many routers do. Or we have a Jeff who's going to say something.
Yeah, so to my understanding, anytime you've got a CMP or you try to load share, you need to look at transport layer to create 5-tuple, and this is where the difference comes in. You cannot read this information. You have the option. You don't load share, or you drop, and some do drop.
And we have a Jeff Haas in the queue. Go ahead, Jeff.
Thank you, Warren. Can you hear me?
Yep.
Thank you. So this is the point where we sort of wind back through multiple presentations on IPv6 that's been given over the years. People's routers are built out of systems that have limited windows into the packet, for fast forwarding. The problem that IPv6 has always had with its headers is it's basically a stack of TLVs of varying size, which means you're asking something that's expected to do very fast work to throw its windows around for fast lookups in a rather unpredictable fashion. And the consequence is that many routers, except for trivial patterns of known options, simply don't bother to try to actually figure out what window it needs to get its information out of there, such as the information that Jeff Tansura mentioned. As things move around, you are limiting the options for the routers to basically do a static template to look at the fields to do fast lookups. So this is exactly the predictions that had been made years ago, and we're suffering from them. Thank you.
Excellent. Thank you very much.
Thank you very much.
I think that this one worked nicely as a follow-on from the previous one. And now we have something completely different, which is Ignis on what would happen to a route server if Bgp Sec was deployed end-to-end today. And hopefully Ignis can help me find his slide set.
Should be in your email.
Yeah, just which one is it called?
IETF113-IEPG.
That one.
And
And does it have USB-C? No, that's the problem with it. I've got a clicker, but my machine doesn't have a USB-A port. So you can push the button if you'd like on my laptop, or you can shout next.
Well, I will shout. No. Hello there. Right.
Or one sec. Does anybody have a USB-A to USB-C converter handy that I would trust plugging into my laptop? Actually, never mind. Never mind.
Right. One presentation on 3 titles. It's some experiments and, experimentation with trying to implement Bgp Sec and see how that might perform in the more or less real world, and how the rosy and ideal world of protocol engineering shatters around into the harsh reality of software and hardware engineering. And also the third one, and that's specifically for Job, which mentions route server, because otherwise he wouldn't pay attention to me. So now I feel happy. Next slide, please.
It's over here. So BGP Sec in theory, that's a really simple idea. We do some, we add some cryptographical verification into the AS path. So sign of what we are advertising and verify what we receive from our neighbors. Signature is comprised of three elements: the actual fragments of the path, the identifier of the neighbor to whom we are sending out, and the prefix itself. Well, do some calculation and then do some other calculation to verify that. Next slide, please. If we'll try to characterize the scalability parameters for that, there are multiple dimensions which are relevant in real deployments. So amount of prefixes and the distribution of prefixes to the AS paths, and there's space where things can be optimized here. What is called the fan-out ratio, the amount of the same AS path information, signed AS path information that you distribute to your outgoing neighbors, and how many of those receive exactly the same AS path. And there's also caching. So if we look at the practical BGP implementations, they cache attributes in one or the other way. As with BGP Sec, the size of the attribute is slightly larger than for, say, other types of BGP attributes. Therefore, we'd really like to try to cache the things. And let's see how BGP Sec as the protocol is friendly with that. Next slide, please. If we look at the platform specifics, so in IETF, it's a spherical BGP which runs in a vacuum. But if we look into the field, it runs on specific platforms. And those platforms have specific and real-world, say, restrictions and limitations to the performance. And the main one is memory bandwidth and memory latency. While in theory you can have a lot, in reality, the latency limits what practical amount of memory operations you can achieve. And also looking into the developments in the compute platforms and processors themselves, the scalar processing performance is increasing in a low single-digit % across the generations. And the main increase in compute performance is in making those operations wider. So single instruction, multiple data, or in general vectorization, where you have one instruction which operates on multiple parallel streams of data. From a cryptographical point of view, signature validation can be optimized in certain environments, like validating the signatures which are generated from the same private key might be optimized to a level. That's also more of a domain of the software implementation and less so of the protocol engineering, but that also needs to be taken into the account, and the protocol should not actively preclude that. And if we look into the developments of the compute platforms as such, the increase in the possible compute performance comes from executing multiple parallel instructions and having wider data paths, so to say, an equivalent, or in well, in a more simpler form, it's a wider vectorization. Next slide, please. So if we look in BGP Sec in practice, how does that look from a data structure perspective, and how does that look from a wire image perspective? From algorithms for hash so first thing, the long message, the AS path with all sorts of cryptographical keys, segments, and other identifiers, it's compressed via SHA-2 hash function into 32 bytes, and then those 32 bytes are used as an input into the signature generation. Both of these processes, they are vectorizable. So themselves, they don't have any preclusion for making them in parallel. And this is more of a domain of the software engineering. Vectorization, if we're talking about the contemporary Intel or ARM platforms, has been around for a decade. And yes, we still have problems in the industry overall. There are problems with compilers. There are problems with overall software engineering community awareness to that. This is slowly but gradually improving. And this is basically a free tool that you need to use. Speaking of hashing, that operates on fixed blocks. Block by itself is atomic. If you compute the block, you can continue the next block starting from the same intermediate state that you got previously. Therefore, this opens opportunities for caching hash calculation for certain data. Signature calculation and verification, those are computationally expensive, but it doesn't touch memory. While you have to do more arithmetic operations on a large integers, you can do that mostly as your underlying platform can allow. Whereas for hashing, you are limited by the memory bandwidth. And there are certain ways that you can work around, but the general trend is that the longer your AS path the longer your Bgp Sec path gets, the more time you will spend on calculating the hash value than on calculating or validating the signature. And there's a small illustration in the numbers. In the current specification, it's 100 bytes per Bgp Sec hop. But however, there are some alarming specifics here. The signature block itself is built from two parts, and those parts are 6 and 94 bytes. And 6 is not a power of 2, and that just falls into a direct conflict with what any practical vectorization platform can support. It's either 4 or 8. If you want to squeeze in 6 there, it's possible, but you will lose far more than you would gain in trying to vectorize that. Next slide, please. Looking into how that works into the vectorization and where the saving can come. So on the top horizontally, you have the incoming message for which the hash needs to be calculated. And Bgp Sec is recursive. You need to do that validation for each and every intermediate hop. Therefore, what you do, if your platform allows for efficient gather or indexed load operation, you simply point out the offsets from which to take the data, and then this is a middle green part, and the time flows from top to bottom. You calculate in parallel, for example, for 8 or 16 lanes. That's one instruction and 8 or 16 instances of separated data. Within the latency of the longest block, you have multitude of bandwidth. So it's a little bit slower than the scalar version because, well, you don't have branching. Some implementations don't support a rotation, which is needed for SHA-2. Therefore, you need to implement that yourself by multiple shifts here and there, and then combining the result. Overall, it's around additional 20% of latency, but this gives you roughly 15 times the overall throughput performance. Therefore, if your implementation allows, you can easily talk about the order of magnitude speed up for signature generation and validation. And then the yellow part is the actual key generation or signing or validation part. The same rules apply. You have multiple entities being processed in parallel. Even if the key actual key length is a little bit different by a few bits, this is purely an implementation aspect of how you can do that efficiently. So the outcome of this, you can get substantial increase in performance if your data structures allow for that. Next slide, please. And here we are coming to the second problem of, or second real-life aspect of Bgp Sec. On the top, you see the wire image. And in Bgp Sec attribute, first you have an array of path elements, then you have an array of signatures. Wherefore, the specification itself asks for the hash to be calculated in sequences. So you have path signature, path signature, path signature. And that means that for that incoming attribute which you received, you first need to copy it around, then calculate the hash and signature, and then copy it back again into the format which will eventually go onto the wire. Touching the memory and copying the memory, yes, you have caching system. You have automatic prefetch there. It works if your algorithm is friendly to that. But if you are reaching up more than 1 or 2 cache line forward or backward, in general, this algorithm cannot cope up with that. And you start to lose latency basically for nothing. Signature generation and verification, well, they are computationally intensive, but overall, that's not the main problem. The main problem is that in order to have the hash over which to sign and which to validate, you need to spend really excessive amount of time just because protocol is not necessarily friendly. Next slide, please. The experiments. So what has been experimented with? Let's take the realistic real-world distribution of prefixes, prefix to AS-path ratios, the fan-out ratios, and the overall setup was that it's 24 hours of BGP updates taken from multiple public sources. That is parsed, different AS-path, only AS-path attributes taken out. It's on the order of 75,000 different ASs. The assumption is made that one AS equals one router. Therefore, there's one pair of keys generated per AS. All that is pre-computed in advance. Then all is fed via RTR into the device under the test. Then based on that incoming data, BGP sessions are kind of brought up, and all of that is replayed into the device under the test. And device under the test feeds everything back with the fan-out ratio of 90% to a receiver. The summary outcome of that, it works. It actually takes, for specific particular implementation in a particular environment on a particular platform, it took 34 minutes for this to converge from the start to the beginning, from start to end. Comparing that to the plain BGP without Bgp Sec, that's 1 minute 20 seconds. And well, I think we can live in certain, at least in the beginning of deployment, or in certain, well, in certain engineered aspects of network design, we can live with half an hour of the initial convergence if you don't need to bootstrap the whole of the network all the time from the beginning. But if we can do something better, maybe we could. Next slide, please. So if we try to look into the whole kind of the situation around Bgp Sec, so is it really broken? From a security point of view, no, everything works fine there. But it's not very much practically usable as it is today. And now two main problems. If we are looking at the layout of the data, Bgp Sec also signs the destination ASN for which we are advertising that prefix. The problem is that AS number is in the very beginning of the field over which the hash is being calculated. That means that if we are spreading out the same AS path to, say, a large number, 100 as an example of neighbors, we need to recalculate the hash 100 times. If we move that field, for example, to the end, that means that we can calculate it once and pre-cache for for the majority of the blocks, and only recalculate 1 or 2 remaining blocks, which are also changing with each prefix. The longer the S path gets, the higher the savings from that are. The second problematic aspect is the actual wire image. We have data layout on the wire and data layout that is being processed really incompatible. And that means that you need to receive something, reshuffle, do the thing, then reshuffle again and send it out. This can easily be avoided. Next slide, please. So what can we do about that? Let's look at the reality. Bgp Sec is, well, at least the current specification version 0. It doesn't have real practical deployments. Well, there are some experiments, there are some experimental implementations, but there are no significant or substantial deployments. The protocol itself is versioned and it has certain hooks for extensibility. Therefore, we practically can talk about trying to extend or fix certain things. Doing a new version, and then within Bgp Sec, there is a mechanism which allows for algorithm change. That mechanism right now identifies only the algorithms themselves, so it's SHA-2 and prime 256. It doesn't say anything about the format over which it operates. One of the possible ways for another version of Bgp Sec would be to extend this algorithm identifier to cover the format of the data which is being processed. Whether that's the same meaning of the identifier or the separate, that's, I think, an open question for a discussion. And also, the wire image asks for changes to make it simply friendlier to the implementation. Talking back about the experiments, so those 34 minutes, if these couple of changes are implemented, they converge into something closer to 4 minutes, which is probably a rather substantial reduction in the overall load. Next slide, please. So that's a summary. Again, that you have the hashing and the signature part spread around over a set of different elements which are scattered around. And that's not very friendly to the implementation aspects. So next slide, please. Discussion. Do we care about this?
And we should probably keep it short, just
Yeah.
beginning.
Okay, so Kiriti, this is my first IEPG meeting, and I came to listen to Inyas, so thank you. It was worth it. I want to pop up a level. If you go to slide 8, he talks about, we should take the specifics of the compute platform.
1, 2, 3,
There's a-
4.
Yeah, it's down in the corner.
Not on this screen, it's not.
Oh, okay. One more.
There we
That's
go.
it.
Now I can see him.
So, take protocol engineering needs to take software and hardware specifics into account seriously. I think this is something we need to do in the IETF, not just here. We're talking about changes to MPLS,
Yes.
and we need to do this. But the word specifics bothers me. I think there are principles. For example, the last thing you said about take the AS number and put it at the end instead of the beginning. I have no clue what you were talking about. But that seems to be a change that is independent of specifics. And so we need to really look at how can we improve, whether it's wire rates, wire formats or processing in the forwarding path. We need to look at higher level things and say, can we do this in a way that we are taking those into account? We can't say this works well on this particular platform or works very well on this Broadcom chip. But I think we still need to do more than we are doing today in terms of, this looks like a nice wire format. let's go with it. And then we get 34 minutes of
Yes.
inviting.
So quickly, this is basically in a context that vectorization is a commodity functionality on the compute platforms today, has been for more or less last decade. Take x86, take ARM, take RISC-V. Those are the three generic purpose platforms which are relevant in the industry. They all have that in one or the other usable shape, or will have.
And I'm cutting the mic line, and if we can keep the question short. Cool.
Job Snyders, Fastly. You asked whether people care. I would like to raise my hand. I think it is interesting that you observed that from a security perspective, it's okay. And I think that stems from the fact that there is not much to take away. It's the most minimal thing that we could do at global scale, assigning prefix, path, and target. The suggestions you make to reshuffle the layouts, it's probably not too late. And there's another interesting mitigating aspect of deployment in the real world that might be underappreciated. I suspect that Bgp Sec is used on Bgp sessions that are most valuable, that have the highest local preference, are shuffling the most bits over the wire, and have the least BGP state. If I look at my employer's network, the most important links are not the links towards full tables. So from that perspective, I am slightly optimistic that there is a lot of value in working to deploy Bgp Sec in its current version, and in parallel work to optimize the current version based on research as what you presented just now, or other operational observations, and that there is some leeway in how the deployment actually happens. So if I compare, say, route origin validation, I think most value stemmed from the fact that the core of the default free zone started first, the so-called tier ones. But I suspect Bgp Sec's value comes from deploying it at the fringes of the network, say hash boxes embedded into people's network. But thank you for sharing this.
Justin, sir, so thanks for doing the research. It's very timely. So the situation is 2 weeks ago, FCC, at least in the US realm, asked us, how come you haven't deployed Bgp Sec yesterday? How come we are so insecure? Probably people live in the US, you've seen 2 weeks ago, FCC published kind of request for information about BGP security. So when I go to him and ask, where's BGP security? He says, you need to buy new hardware. Even so, whatever I buy today brings at least Broadwell class Intel, right? So I know every vendor has implemented at least beta code to do BGP security. So whatever I found is not a secret. I mean, it's basic software engineering. Can we create some kind of design team here to take this actually seriously, bring it back into implementation, and get something working? Please don't leave this presentation here. Bring it to CyberOps or somewhere.
So this is on the agenda for CyberOps in a slightly different message, probably. Now, for practical deployment of BGP Sec, there are two parts: BGP Sec, the protocol, and the supporting infrastructure of BGP Sec. And the second problem is probably harder. Well, at least it seems now. Right? So it's not enough to have a perfect protocol, which is not conflicting with the platform specifics. You also need other things around. And yes, there's quite a large amount of work.
Sure, but we need to start.
Yep, somewhere. But I think we need to cut the mic for now and can maybe carry out the discussion in CyberOps. Cool. Thank you very much. Just for time. Lenny.
Thank you.
Lenny. Oh, there we go. Let me just find your slides. Okay. This one promises to be entertaining. Slides. Here we go. Share. And I will grant you the ability to change slides. You have 10 minutes and we will start them now. Thank you.
Thank you. So I'm going to talk today about a recent draft that we submitted on regional internet blocking. We are presenting this in int area and plan to see if there's interest there to adopt. Before we get started, just a few disclaimers. The content in this draft represents ideas solely of the authors and does not reflect any of the positions or views necessarily of any of our affiliations. Likewise, this kind of goes without saying for those familiar with IETF processes, but for those who aren't, this is an individual contribution and does not represent IETF consensus. All right, we got that out of the way. Now for some of the fun. So the first question is, a little bit of background and motivation on why we wrote this this draft. In light of recent geopolitical events, there has been discussions in various circles, both technically and non-technically, politically, on the concept of blocking internet connectivity for a region. Kind of the internet version of economic sanctions or connectivity sanctions. So what we wanted to do is to describe, well, what would that look like? What would be some of the ways in which this kind of blocking could be accomplished? And what are the implications? Positive, negative, what are the advantages, disadvantages? What are the potential consequences intended and unintended? The audience, the target audience for this document is policymakers as well as the general public. Basically, everybody who's not in the room right now or in this working group, but is interested in understanding what we who are in the room kind of have as common knowledge on the topic of filtering, blocking, and what it would look like and the kinds of considerations one should know about if one wanted to block connectivity for a region. The idea here is that policymakers do depend on good, unbiased information, sober, clear, technical information on what is possible, how it works, and would it actually do anything. So that's kind of the idea behind this, is to discuss the potential intended or unintended consequences. In terms of what this document is not, we are not advocating for or against any particular policy or position. We are not trying to inject political opinion as to whether or not this is or is not a good idea. We're just trying to really, report the news. This is how it would work. This is some of the things it might do, so that people who do want to make an opinion on these things could make perhaps a better informed opinion on the matter. We're not analyzing the ethics of such an approach. We also, obviously, there is an ongoing conflict right now that inspired the writing of this draft, but we would like this to be generic enough that it is applicable to more than just one episode. This is probably not the last conflict that's going to occur where this topic might pop up. So hopefully this could be useful both now and in the future. Also, this is not meant to be a guide on how blocking works or what is blocking, or protection against security threats. Let's say that there was threats coming out of a region and you need to protect yourself from that region. This is more of sanction purposes. We're not trying to also describe kind of a how-to guide on weaponizing the internet. We're not letting out any secrets. This is pretty well-known approaches, and you'll see, nothing groundbreaking here. These are pretty well-known approaches that operators use fairly commonly for legitimate blocking purposes. We also didn't go into a malicious attack approaches and kind of a survey of those. That's an interesting topic. It's probably worth discussion. But that's such a broad topic, and it's outside the the scope and the expertise of the author. So we left that outside the scope of this document. All right, so the meat of the document. What's actually in this document? We start at the physical layer and work our way up. Again, nothing groundbreaking here. What would happen if you disconnected cables? And then we move on to the routing layer, control plane, what it would look like to de-peer someone, what would be the results of that. There's route filtering based on prefix or ASN. There's data plane filtering, things like GeoIP, access control lists. And then we looked at DNS, what it would look like to, some approaches might be removing delegations to TLDs and other relevant domains. Also, blocking resolution requests that might be coming from a resolving name server or end hosts that might be in a region. The next area we examined was, all right, gaps in efficacy. Would this actually work? What would this do? Some of the intended and unintended consequences. So there's the obvious, blocking connectivity for a region may be counterproductive to the aims of a policymaker. Perhaps a policymaker might want messages to actually get in and out of a region, and blocking that connectivity might prevent that. They may want perhaps certain parties within a region to be able to communicate freely, because those, say, oppositional parties might be sympathetic to the views of the policymaker. So again, might be a reason, to be aware of that, this might not happen if you do block connectivity. Also, it may end up empowering, a party that is, the target of sanction, allowing them to, that, party to or regime to perhaps consolidate their power by not being able to allow some of the information that we just mentioned to go in or out or within a region freely. The thing to keep in mind is the network is amoral. It does not discriminate between, it just transmits bits, whether they're good or bad, whether they comprise good or bad messaging. The network just pushes them through, from one place to another. Also, autonomous systems and prefixes are not allocated based on geopolitical boundaries. They're loosely allocated on region. And there are registries, but those the registry information can be fairly accurate. Also, things can change. An entity that is assigned a resource like an ASM or a prefix that exists within one region, well, it might move to another region or be acquired by a multinational corporation, that, multinational entity that might start advertising that route or that ASN in a different region. So it's really kind of difficult. There's porous borders when it comes to network resource allocation. Also, the internet is by design decentralized. And that makes it, nearly impossible to completely block a region. That's a feature, not a bug of the system. But you can put a good dent in connectivity and throughput at certain checkpoints. There has been some, prior art in the area. RFC 7754 talks about internet service blocking and filtering, but it's more focused on application level and transport than actual network infrastructure. Also, the purposes are a bit different. It's more like, security, objectionability, and business arrangements, and less so about sanctioning. But there are some overlapping themes. There's a draft in the PEARG working group on censorship. And again, this is more focused on censorship by a regime within their borders rather than blocking their region stuff coming out for the purpose of sanctions.
And just a quick
there
note
also
that
is a
we're
little
almost
bit
out of time.
Sure. Just finishing up. Like I said, we're going to be presenting this into area, looking for adoption. First question we'll ask is this document useful? Is this interesting? Is this worth working on? Are there other things we missed? The question of BCP versus informational, and review and comments. And if you have produce to throw, show up at Interia. with that, I'd be happy to answer any questions if there is time available or if there are any questions available.
Excellent. I guess more questions will happen in area because I'm suspecting there will be some. Thank you very much, Vinny. Yep.
If you want.
One quick question. Make it really short.
Quite obviously, any idea of blocking is in conflict with the IETF goal of making the internet work better. Figuring out exactly good information about effects of blocking quite obviously makes a lot of sense in this context. Talking about blocking, however, can trigger with certain parties the idea that, well, okay, they should actually think about it. And myself, I have noticed over the past years a couple of events where parties were starting to think about sovereign internets. And kind of part of that, quite obviously, has been motivated by preparing against the threat of being blocked in some way. And regardless whether a technical paper explains in detail the bad effects of blockage, and in the end suggests that blockage should be avoided, the mere existence of such papers can be used by parties who are interested in segmenting and, well, okay, maybe reinforce their empire of lies. So one has to be extremely cautious when doing such papers to figure out ways, and that these ways need to be extremely clever to avoid feeding that evil track of arguments. Thank you.
Thank you.
All fair points, and you know, we're not trying, again, we're not trying to say this is good or this is bad. We're just trying to say this is what would happen to the best of our ability if one did this, to let others decide if this is good or bad. And we, like I said, I don't think we have any trade secrets or network secrets here. There's really nothing novel here. This is pretty pedestrian descriptions of what is going on. So I don't think we'd be planting any ideas in anybody's mind, but thank you for that feedback.
Thank you. Okay, and Willem.
Yes. So this presentation is about my efforts in setting up a useful RPKI beacon, useful for measuring route origin validation, and also hopefully useful for you. I was searching on the internet for a picture of a lighthouse or a beacon that would lure ships towards it, and a vortex in front of it. And you can see that I found a picture like that. And this is a picture of the excellent rock album, The Maelstrom Ascendant, which also has a accompanying book, and of the Sydney-based rock artist Duncan Smith. And by saying this, I have his permission to use this picture. So thank you, Duncan. Next slide. So I also made a good effort to get this presentation here at the IEPG. I submitted 3 times or so, I think. And because, you know, I had to set up an RPKI beacon. I will tell you later why. But I'm not really an RPKI expert, but I know that you all are all RPKI experts, so that's a really good audience. And I'm also a little bit nervous because you are all RPKI experts. But yeah, I'm hoping to make some RPKI beacon friends here that can help me, with this effort and tell me if what I'm doing makes sense and how to make it better and how to make it more useful. And yeah, well, I will tell you later, but I could also use some additional IPv4 resources for some specific aspects of this beacon. Next slide. So here I do sometimes do DNS measurements. Here you see a picture. That's me. At the taken at the Internet Measurement Conference in 2019 in Amsterdam. We were awarded for a research paper on the root case cable over. And during that conference, there was just the hijack of the Ethereum wallet. And that was by a route hijack. Right? The authoritative service of Route 53 were hijacked, and the resolvers were not protected by route origin validation. So it was clear to us that it's important that we would do these measurements as well. And we learned at this conference that there was a person called Job Snijders who had the RPKI beacon. And we spoke to him and asked him if he could use his beacon to do this kind of measurements. And Job allowed that. And thank you, Job, for that. That was really great. And we started to do the measurements to measure the uptake of route origin validation of DNS resolvers since 2020. But unfortunately, the beacon didn't stay for a very long time, or it stayed for almost 2 years, but we had to look for another beacon. So yeah, that's the reason for this effort. Next slide, please. And at the beacon at the time was the RIPE NCC RPI web test. There was the Check My DNS effort from the DNS org. Our own validation measurements. Next slide. And the beacon was set up. It had invalid prefixes announced from the beacon and also valid prefixes for reference. Next slide. So the effects of this setup were a bit like this. So if you would be on a validating hop, then you would not end up at the beacon. And also, if you would be on a invalid or not validating hop, but surrounding by validating hops, then you would also not end up at the beacon. The next slide. So this gave some difficulties with doing the measurements in that it was timeout based. Now, if you can reach the valid, but you cannot reach the invalid, then you have to wait for timeout. And also, route and origin validation is to prevent route hijacks. And so since the invalid prefixes were not announced anywhere else validly, you could ask yourself if it was if it looked like a realistic route hijack. Next slide. So for the new beacon, we did it a little bit differently. We announced a /23, less specific, from Amazon, to be precise, and a invalid /24 from that less specific from ColorClue, which is really convenient because you don't have to wait for timeouts. And maybe it's also a bit more realistic, but maybe not. Maybe for the most realistic situation, you would have 2 /24s. Next slide. Yeah, so here you can see the ROA, the route origin authorization for the /23. And just for the record, I also made one for the /24, but with for ASN 0 to officially say this is invalid. Next slide. But you know, it's still really hard to determine which hop does the actual validation. And it also has the peculiarity that if you are in a network that is validating, this you might still reach the invalids. And why is this? Next slide. Because on the path towards the less specific, the lighthouse, so to say, you might bump into a non-validating hop, which is luring you into the vortex. Next slide. So taking the picture that I used before, it's all the white things close to the lighthouse are good, but if you're crossing a non-validating hop on your path towards the lighthouse, then you end up at the beacon. Next slide. Yeah, well, so all the apps that used the earlier beacon, they all moved to the new beacon. So it was really easy to do a API test for resolvers, because you just run two authoritative servers. One has a zone that says, hooray, you're protected at the valid, and one says, no, you're not protected at the invalid. Next slide. So at the invalid beacon at Coloclou, I also created a RIPE Atlas software probe, which uses the invalid resources and has the command path on a valid resource. So people using RIPE Atlas can use the beacon as well. Next slide. The beacon is also at the NL ring. If you're on the NL ring and you're secure shell to the NL Labs ring node, then you will see this text that you can enter a network namespace with the invalid resources, but with the command enter invalid net ns. Next slide. And this is how it works. You can see, so if you secure shell there, then initially it just uses valid resources. You can ping the website of the IETF. And after entering the invalid network namespace, you cannot. But you can. It still does work because you can ping NL Labs, for example. Next slide. So this can be used to measure other things as well, like, for example, authoritative service. But the question is, should services be protected by route origin validation? Because they're not actually connecting to other servers on the internet. Next slide. So this is it. So does it make sense? Is this a good way to do it? What tool would you need to do it? And how can I make it better? So if there are any questions.
I'm in the queue, so I will 18, 17, 16, 15, 14, 13, 12. There we go. So 12, I think that's the one. So this is a good point. If you go anywhere where, you pass through a validating network, which then takes you to a non-validating network, you still end up at the bad place. But maybe that's actually the correct thing to be showing, because that's what would happen in the real world. So I don't know if the right thing to answer is that you're protected or not, because the network you're using happens to validation, but you still end up in a sad place. So I don't know what the right thing is. Anyway, we have 3 minutes left, so I will leave the queue.
Is this? Yeah, it is on.
Ben, work online. So that's an important observation, and I think the reason that it's important is because I was struggling for most of your talk to identify exactly what you're trying to measure. And if I understood correctly, what you're trying to understand is the extent to which DNS resolvers are susceptible to following a route to a hijacked authoritative DNS server. That's fundamentally what you're trying to measure.
Initially, yes.
Okay. So I think that I think in order to work out what you need in the way of a beacon, you need to be concentrating on what the most likely attack against that traffic exchange is. And I don't think that it's a more specific hijack. I think in most cases, most people that are operating DNS, authoritative DNS servers are already announcing 24s as for v4 in order to, in order to mitigate the possibility of people being able to, sneak longer non-RPKI related announcements into the routing table. So I think the most likely attack is someone spoofing the origin.
Mm-hmm.
And the difficult bit to defend against is the fact that you're then relying on AS path length for selecting the correct the correct destination, and that will show a pattern that's similar to the one in your map, but will be more pronounced. You'll get more resolvers going to the wrong destination. So that's what I would be trying to mimic if I was you for that measurement.
Yeah. Yeah, it's indeed that, but it's also trying to identify which hops are doing validation.
If the question or answer, if you're trying to tell the operator of a recursive DNS server, are you likely to be seeing safe results or not? I mean, that's a binary question. The why is interesting, but it's not as important as the yes or the no, right?
Mm-hmm.
The only other observation I had is your AS0 rower is redundant. It's not doing anything. It's just noise.
Yeah, it's just for administration.
Thank you. And Jeff, you're up next, and let's keep it short. Willem, there's still one more. Jeff.
I'm trying to unmute my audio. Thank you. The problem is, Willem, that the more transits deploy, the harder it is to reach your beacon. And if you have only one beacon, you kind of die well before it sort of ceases to be useful, because deployment in transit tends to make this weird. We started off in our work with one beacon. We increased it to 4 in Anycast, and then we started to glom onto Cloudflares, because in actual fact, it really depends on what you're trying to measure. And what you're trying to measure depends on what you're trying to prove. Oddly enough, everyone must do cloud origin validation is actually not that useful. We can get 95% of the result if, let's say, 6 transit networks do validation and no one else does. Because if paths go through a small amount of the core and the core is doing validation dropping, it actually doesn't matter what the stubs do. And this interplay between deployment, right, and filtering hasn't been studied at all in the areas of RPKI. We've adopted the mantra of everyone must do it. And that mantra is meaningless. It creates a whole bunch of wasted effort with only marginal return. If everybody else does ROV filtering, I don't have to. And you can actually extrapolate that statement outward. What's the minimal spanning set for ROV filtering for the maximal benefit? And that statement hasn't actually been studied hard. The problem is, in a nutshell, single beacons don't make much sense anymore, because as we progressively deploy, they become progressively unreachable because of transit, not because of ROV filtering. And so you really need to rethink exactly how you do this to make the beacon useful if you want to trace it back to the source. Thank you.
Okay. Thank you.
Great. Thank you very much.
Okay.
Sorry we're out of time. Last one on the agenda is Mr. Tony, and I will give you slide privileges. Let's make sure this works. Can you change the slides?
Thank you.
Excellent.
Hi, this talk is a footnote on CIDR. Those of you who are of an age may recall what we decided a long time ago. Started talking about aggregation, and we started talking about doing continental and regional aggregation, but nothing really happened. This talk is about bringing that up again, not because I want people to start doing it, but I wanted to document some thoughts about how to do it before I end up retiring. So what's changed since we started doing CIDR? One thing that's surprising is we've started leaking more specifics all over the place for traffic engineering. And that's caused a great deal of noise in the routing table. It would be really nice to clean these up. And it would be very effective to clean these up at a distance, because frankly, once you're at a distance, the more specifics don't add a whole lot of value, frequently none. We have a new idea on how to think about aggregation. I wanted to write this down before it gets lost. And we talked a lot about proxy aggregation long ago. I'm going to bring up another idea, which is doing unilateral remote aggregation. So in traditional aggregation, we have an ISP. He has a prefix P, and he filters out all the more specifics and just distributes P everywhere. What I'd like to talk about now is a new concept, an abstraction naming boundary. And that's just the edge of the ISP where prefix P exists. And another concept we want to call an abstraction action boundary. And here I'd like to give full credit to Noel Chiappa, who came up with this idea long ago, and it never got written down. The basic idea is that you don't have to do aggregation right at the same place where the prefix actually exists. You could do it several hops away. And in this picture, you can see we're leaking more specifics outside of the abstraction naming boundary, and then actually taking action and creating the abstraction farther out at the edges of the oval. This could be 1, 2, 3 AS hops away. What happens if you do this? Well, suppose ISP A is the owner of the abstraction, and he's leaking more specifics all over, and ISP B now does remote aggregation. Well, the traffic's going to follow the more specifics. So ISP B suddenly is going to see a bit less traffic. He's still advertising P, so ISP A is still being served, but traffic is naturally going to flow in the alternate directions. Okay. If you do this, this is not necessarily a horrible thing, not necessarily a good thing. Where you do this inside of ISP B actually matters. Does ISP B care about the traffic engineering that ISP A is advertising? And it can, if it does it on ingress, it gets rid of some traffic, it gets rid of some routes that it's going to carry. If ISP B does the aggregation on egress, they still get the traffic engineering benefits, but has a few more routes to carry. So could we do this to higher levels of aggregation? So we have a bunch of regional aggregates. The RIRs have nice prefix blocks, /12s, for example. And could we remotely aggregate these? And if we do that, we take out all of those annoying traffic engineering more specifics. We take out organizations that only exist within that RIR's region. Where is it we would put the abstraction action boundary? And this is something you have to look at on a case-by-case basis. If you put it too close to the actual abstraction, too close to the region, you're going to break traffic engineering. And if you go too far away, you're being wasteful. Those more specifics are transiting too far away. And this is a case where it'd be very, very useful to have a little more field input. So I'll throw that question out to you guys. Just as a reminder, this is what our RIR map looks like. You'll notice things don't quite correspond to continental boundaries. If you wanted to say, have a remote abstraction action boundary around RIPE, you might draw this line here. And this is a little bit farther away, just so that it gets the traffic engineering. You could also do continental aggregation. And I'm going to pick on Jeff here. Okay. Intercontinental links are relatively rare comparatively. And so we very much want to traffic engineer those intercontinental links. But we do want to do, we could put an abstraction boundary just on the other side of those intercontinental links. We would also kind of like it if the RIRs would do continental addressing for us. So you can imagine, suppose we want to throw an abstraction of Australia, and we might put the abstraction action boundary several hops past the transoceanic links going to Australia. Okay. Yes, we know that there are some RPKI issues, and we have to figure out how to do that with aggregation. And that's something we have to work out. Okay. So love to hear what people think about this and whether this is useful and whether they're willing to try that in the field. Thank you. Any questions?
Yeah, hi, Nalini Elkins, Insight Products. Okay, so just one anecdotal data point from somebody that I'm working with is a large organization in the United States that has a global presence with probably people, I mean, all over the world. And we were talking to a particular RIR, and they said they would be willing to give them address ranges for globally. So I mean, I don't know how this fits into your picture, if it does, or can you comment? I mean, I'm just saying, just one data point. I'm just, you know, I'm just wondering how it fits into your picture here.
It doesn't fit in. We know there are lots of organizations with global span that are injecting their prefixes from many, many points, and those are not good candidates for aggregation for obvious reasons.
Hi, Tony. It's Jared. I am curious what you're trying to optimize here. Are you trying to optimize the fib or the rib?
I'm trying to optimize both. So call it rib.
Okay. Yeah, because I think I think it's very important to talk about the two separately. So the first thing is that, you know, inside of my employer today, we actually have a solution that we use to go and ensure that we don't, you know, that traffic tends to be heavily regionalized when you talk about a global footprint. And so we don't have to, we may receive all the paths in, you know, our rib in, but that doesn't mean that we actually need to carry all those, you know, all those paths in the hardware. It's also possible that many of them have the same next hop. And so that we can actually do localized, you know, optimization. I know a number of vendors have done either internally fib compression work or otherwise to ensure that, even though the rib may have more in it, the fib, actually can run a lot leaner from that perspective. So there have been many different, both software and hardware optimizations done there. I think the other thing, just kind of looking at this just generically, is I think this makes a lot of sense in a case where there's a lot of national, aggregators or international aggregators, but that's actually largely not the case anymore. If you're actually looking at the internet today, and Jeff Houston's, talked about this some in the past, it's largely, how do I get to the largest N cloud or content providers within my region? And almost no other traffic, there's not a lot of long distance traffic, in that regard anymore. And if you look at what enterprises are doing, they're largely integrating into one of the cloud operators, and purchasing direct interconnects for on-ramp, off-ramp activities. And so the need to do this, there's a very interesting question, around this, is how much is this actually really needed per se? And at the same time, I also want to comment is that I know my employer is really bad about polluting the route table. And we're trying to, I'm working hard to try and address that, because we largely had a lot of things globally that were very unique, discrete sites. And over time, my long-term goal is to continue to advertise out those local, more specific routes to ensure that we attract the traffic in the right locations. But globally, not everybody needs to see those routes. And so we don't need to advertise those all globally, which may end up with much wider divergence in what a local versus global table looks like, but that is heavily optimized around the locations that need to get the routes. And so I think that this is, just looking at this at a high level, I think the idea of where these aggregation points are is very interesting, because I think they're not where we would have thought they were, 25 years ago. So I don't know if you have any comments or responses to that, but I think at least at minimum, the fib optimization seems an area of potential interest.
Yes, fib optimization is of interest. We talked about that, and some people have implemented that. We still have lots of people who are having scalability issues at the rib level, so I'm very much more interested in trying to address that. Yes, I'm well aware that traffic is orthogonal to routes. That's fine. I'm still trying to optimize routes. Rudiger.
Rudiger Volk. Hi, Tony. Simple question. Are you thinking about any cooperation of the owners of address space or routes?
Well, of course, cooperation is always welcome. If people want to be aggregated remotely, that would be a very interesting proposal.
Okay, in general, you are not expecting that as a basis for moving forward.
No, I don't think that's a requirement. I would be very interested in seeing what happens in the field experience, both with and without the cooperation.
With my simple mind, I feel that without cooperation, the current existing universe is not really expected to get a solution in your direction. You smart guy might have ideas of what to do. What concepts to use in signaling and so on for getting cooperation information into this.
Well, again, I don't think cooperation is required. I don't think you actually break anything if you don't have cooperation and you just go off and do remote aggregation. As long as you're advertising the aggregate, you are continuing to provide connectivity, but you are shifting traffic away. I realize that alone could be contractually a problem, So people should think about that, but I don't see that it actually breaks anything.
Jeff Censura, maybe just a data point. At least my employer, we already have a service that's intermediate between internal BGP speaker or external peering. We already have this layer that does aggregation both externally and internally. So pretty much what you are proposing here is already done. I would think that other clouds do as well.
That would be very interesting to look at.
Excellent. Well, thank you, everyone. I think that this brings us to the end of IEPG, and we actually still have 10 minutes left. If I'd planned time better, we could have done some more of Willem's questions. But we will almost definitely be meeting again in Philadelphia, assuming that we actually meet in Philadelphia. So I'm trusting everybody will have all sorts of exciting presentations for us then. And enjoy, where are we? Vienna. Enjoy Vienna. Thank you, everyone. I don't know how, now that I don't know where you stole this from, but thank you. Awesome. Perfect. Thank you, sir. I don't know how I logged Tony out. Wasn't me. Wasn't me. Yeah, maybe. I think so, yeah. Hopefully it's not. I'm likely it's just something small. Yes, yes. Hello, how are you?
Yeah. Good. Cider. Lorenzo was actually asking questions plenty in a couple of hours. What do you think we should try to squeeze anything about the BGP drop into the 6th of tomorrow if it's possible?
I think probably not. Because we haven't discussed it. I mean, it would be nice if we could have, but we didn't really get our lives well enough organized.
Okay.